Good morning. So today we're going to be talking a little bit about continuations and how we've implemented them in the hotspots VM. So yesterday we heard about virtual threads. I think by now everyone knows what virtual threads are. These are threads that you can have lots of. And they're implemented in user mode in the JDK. Now, what does it mean to implement a thread, or rather, what is a thread? So we can think about a thread as being a combination of two things, a continuation and a scheduler. So the scheduler is written in Java in the core libraries. It is essentially just an executor service. We're using the fork-chain pool one. And the continuation part is implemented in the VM, and that's what we're going to be focusing on today. But before we get there, I want to first dispel a common misconception about virtual threads or user mode threads in general. And that is, we use them to help performance. And the misconception is that they improve performance because they have a very fast context switching. And that is not the case. Virtual threads improve the throughput of servers written in the thread per request blocking style, simply because you can have many of them. And according to Little's law, having more threads will give you more throughput. And by the way, I gave a talk, I think it was last year, at a conference called P99. So if you want to learn more about Little's law, and there's quite a bit to learn, it can be quite interesting. So go to the P99 conference website and look for the talk. However, even though virtual threads don't get their performance benefits from fast context switching, their context switching does need to be efficient. And that is not because of its total latency, how much time it takes, but because ideally they need to consume very little CPU time. And that is because, and you realize that once you apply Little's law to the CPU itself. And because the continuation is, because the virtual thread is implemented as both a continuation and a scheduler, both of these need to consume as little CPU as possible to do the context switch. But today we're going to be talking about how we did it for the continuation part only. There are many different kinds of continuations. The one we have in the JDK is categorized as a non-reentrant, delimited, asymmetric, multi-prompt continuation. No need to know what that is, but you can look it up. And the interface looks something like that. And a continuation is essentially a runnable that can suspend itself and later on be resumed from the last point it's suspended. So a continuation has a body, that's the runnable it runs, and has a scope. The scope comes from the multi-prompt thing that has to do with the prompt. We're not going to talk about that, so you can ignore it. And has two interesting methods, run and yield. Run either starts the continuation, starts executing the body, or resumes it, and yield suspends it. And those scopes, by the way, they allow us to nest continuations inside one another. But that's the last thing I'm going to say about those. So how would it work? This API is not public, but if it were, we're inside the JDK, this is how it would work. So we have a continuation here, and it has a body. It prints something, and then yields, and then prints something else. So the first time you run it, it executes everything up to the yield, and it will print the word before. Then it yields, and when yield is called, run would return. We suspend the continuation, and run returns. And at that point, is done says false because the continuation is not completed yet. It's just suspended. When we call run again, rather than starting anew, it will continue from where we stopped. And then it will just print after, and then is done is true. So the way to think about this is, I think that part is quite cool. When you call yield from inside the continuation, that causes the run method to return. But when you call run, that causes yield to return. So when you call run the second time, yield returns and would execute the next line. So calling run causes yield to return, calling yield causes run to return. I want to introduce some terminology. when a continuation is being executed, when the body of the continuation is running inside on some thread, we say that it is mounted, and when it is not running, when it's suspended, so when we're talking about virtual threads, that's what happens when a virtual thread is blocked on I/O or some synchronization construct like a lock, we say it is unmounted. So I said before that a thread is a continuation plus a scheduler. So let's see how the most interesting things we do with threads is to block them. That's sort of why they exist. And almost all the blocking inside the JDK goes through this class Java utility concurrent lock support, and this pair of methods called park and unpark. Park blocks the current thread, and unpark unblocks some other thread. So how's that implemented? So at runtime, this is a dynamic test. We see whether the current thread is virtual or not. If it's not virtual, we do a syscall and ask the operating system to suspend. That's a platform thread. We ask the operating system to suspend the current platform thread. If it is virtual, we yield the current continuation. So a virtual thread is made up of a continuation, and we just yield it. And at that point, when we yield, we said run returns, and run was called by the scheduler. So the scheduler thinks the task is done, it will pick up another task and execute that. When we want to unpark a thread, if the thread is virtual, all we do is we take the virtual thread's continuation and submit it to the thread's scheduler. It's from the perspective, the scheduler doesn't even need to know that it's executing continuations. For all it knows, we've just submitted runnable. It's a new task, but the next time the scheduler calls run, decides to schedule the task and run it, what's going to happen is that the continuation is going to continue. Continue from where? From the yield point. So the next time the scheduler, so after we submit to the scheduler will call run, yield would return, and then park will return, and that is essentially blocking, right? So park blocked, and now park returns, and everything goes on. Okay, so what do continuations actually do to stacks? Now, what I'm going to show is not necessarily what the implementation actually does. We'll get into that a bit later, but sort of a mental model of what's going on. So we have a thread, and what we have here is a number of frames running, and in all my slides, the stacks grow downwards. So every time we call a method, it will add a frame below. So we have some code running, and then at some point, we start a continuation. So we call continuation run. And then inside the continuation's body, we call method A, that calls method B, that calls method C, and then C calls continuation yield. And at that point, we need to make run return. So we essentially pop all the frames inside the continuation A, B, C, and yield to make run return, but we need to be able to continue them later, so we need to put them aside somewhere. So it's as if we transfer those frames over to the side to some continuation object thing, and then we can return from run. The next time that we mount the continuation, that we call run again, the opposite thing happens. We want yield to return with all the state of the continuation, so it's as if we take all those frames inside the continuation and transfer them over to the thread stack, and then we can return from yield. And then we return to C and continue executing. Now, the most straightforward way to implement what I just showed you, the mental model, is to actually implement it like that. Copy the frames. That's like, the first thing you'd try. And if we're talking about copying, I'm going to introduce another piece of terminology. Transferring frames from the thread stack to the continuation stack, the continuation object, we're going to call that freezing. And thawing is the opposite. So we thaw frames from the continuation object and transfer them over to the thread stack. At first you might think, okay, copying is not very efficient. We'll get to that, but it does have an obvious advantage, and that is all the actual execution is actually taking place on the regular thread. So we don't need to change any of the compilers, any of the frame representation. It all just works. And we can call native code. because we're still running inside a regular OS thread. Now, we can't yield, or we can't freeze native frames. That's what we call pinning. But if we don't try to do that, we can just call native methods. They'll return, and everything just works. But it does have a clear disadvantage, and it's not necessarily the cost of copying. It is that the work we need to do every time if we need to copy the entire stack is proportional to the entire depth of the continuation stack. And we'll see why that is a problem. By the way, from this point on, let's forget about virtual threads. Let's imagine they don't exist. We only have continuations and regular threads. Okay, so why is that a problem, that the cost is proportional to the depth of the stack? So suppose we have some framework, one of those big Java server frameworks, and we want to handle a request, and the framework has this handle method, and then, as we know that lots of Java frameworks do, we have lots and lots and lots of calls, hundreds of them maybe, and then it calls back to user code, and what the user code does is read some bytes from a socket, and has a loop that reads bytes from the socket as long as there are more. And the problem with that is that most of the time we're just going to be looping in those newest, youngest 3 frames. But if every time we block, that is what we're running, only those 3 frames. We're just looping inside them. But if every time we block or yield, we have to copy all those hundreds of frames, we're doing a little bit of work, like useful work. The overhead of copying is we need to copy everything over, even though it's not useful. So before we even contemplated actually implementing copying, we knew we had to solve that problem. And we came up with something that we call a lazy copy. And the idea is this. So suppose we have a thread that's running continuation with A, B, and C, and then C equals yield. And the first time we freeze, we copy everything over. And that's fine, because we just created those frames. We worked through them. Creating them was useful work. So we're copying them to the continuation, and then we're popping them and returning from run. Now when we want to mount the continuation again, what we do, we call run the second time. We don't copy everything over back. We just copy 1 or 2 frames. Now, when C returns, it should return to B. But B is not on the stack. So what we do is we patch C's return address and something we call a return barrier. We replace it not to return to B, but to return to some VM code. And then we continue, yield returns, C returns, but now it doesn't return to B, but to some VM code that will store more frames. Another one in this case. So it just copies over B. And then B equals D, and D equals yield again. And now we have to freeze, and now we only have to copy B, D, and yield. And if you think of A as representing all those lots of framework frames, A stayed put this entire time. So we didn't do any unnecessary work. And so now the cost is proportional to the amount of work we've actually done. We only copy over the new frames, and that's okay because those are frames we had to create. So let's say the overhead of copying is commensurate with the actual useful work we had to do. Okay, but what is that continuation object? So we know about frames on a thread stack. What does it mean for them to be inside a continuation? So this is where the challenges began. The most basic challenge is that that stack frames can contain references, pointers, or we call them inside the VM, we call them oops. And because you can have local variables, string local, and that points to some object on the heap, so that's an oop, and that's stored inside the frame. The pointer is stored inside the frame. And that means that the GC needs to manage those stack frames because it needs to trace through those oops. And if it's managed by the GC, we try thinking, okay, so where do we put those continuation thingies? And we realize that wherever we put them, we need to do pretty much as much work as the GC need to do anyway, so they might as well be in the heap. Now, there's another matter pertaining to GC. In fact, you'll see GC has been both the challenge and the solution for many of the things we faced. For ordinary platform threads, every time we start a garbage collection cycle, we say that those thread stacks are roots. So every time we start a collection cycle, we scan through them and find all the oops inside the thread stacks. And the problem with that is that in some of the garbage collectors, it used to be all of them, but some of the garbage collectors do this process of scanning all the thread stacks in a stop the world pause. And that's sort of okay because the amount of memory that we have inside thread stacks is not that big because we don't have that many threads. But that's no longer the case for virtual threads and their continuations because we can have millions of them. And now we can store quite a lot of data inside stack frames. So we can't have them be GC roots because we don't want those GCs to scan all of them every time, certainly inside a stop the world pause. So we want them to be regular heap objects that are not like strings. The most technical point that proved to be the most challenging is that GCs have this invariant that OOP locations must be stable. What does that mean? Inside an object, we can have OOPs and we can have primitives. So we can say we can have a class that has an int and a string. And the GC requires that inside an object, the position of the OOPs must not change throughout its lifetime. So both for object, so the GC knows where the OOPs are, but once the GC knows that an OOP is, I don't know, the offset 4 from the beginning of the object, there must always be an OOP there. There must never be a primitive. And that means that a direct representation, just taking the stack and putting it inside an object, is quite difficult because stacks don't behave like this. Stacks mutate, so we call a frame, and a frame has some locals, some of them primitive, some of them oops, and then the method returns, the frame pops, and another method is called, and that method might have oops in a different location. Maybe it just have ints, maybe it just has ints, and it doesn't have any oops, and now in the same location where previously we had a string, now we have a primitive, and that's very bad. So you say, okay, so let's do something straightforward. The continuation will be, we'll store the frames inside 2 arrays. And if they need to grow, we'll just, like an array list, we'll just reallocate them and double their size or something. So we have a byte array. And into the byte array, we do copy the frames as is with our oops, but the GC doesn't know that there are oops inside a byte array. Then we extract the oops and put them inside the object array. And once we want to store and the GC knows about the object array is stable, right? So all the cells inside an object array always contain oops. The GC knows about that. That's not a problem. And when we want to thaw frame, we'll copy it from the byte array and then patch in back the oops from the object array because those are the ones that have been fixed by the GC. Now, what does a frame look like? And how do we know where the oops are? So a frame has some data in it, including some oops. But the only kind of metadata that tells us anything about what that frame is, which method it belongs to, is a return address. And in order to know anything about it, that return address points to the method's code. That code lives in the code cache, where we're mostly going to be talking about, going to assume that most frames are compiled. It lives in the code cache, and from the return address, it will point somewhere in the middle of the method. We have a search algorithm to find the associated metadata with that method, and that has the frame size and the OOP map. The OOP map says, at that point in time in the method, this is where the oops are in the frame. And that OOP map is stored in some compressed data structure that we could parse and find the oops. In fact, we need to find that metadata just to walk the stack because we don't even know how big the frame is. We don't know where the caller frame unless we look it up in that metadata. That's not written anywhere inside the frame. All we have is a return address. So like I said, to copy, we take the frame, just copy it, and then also the oops, and on the way back, when we thaw, we copy it back and patch back the oops. Now, the cost there, we tried doing that, the copying barely registered. The copying itself was less than 1% of the time. Most of the time was finding the oops and parsing the frame, finding the metadata. So we knew we had to make that much faster. So one thing we tried to do is how to find the metadata from the return address quicker. So what we did was, the return address points to the method code. It points to the instruction following the call instruction. So if A calls B, right, so we have a call instruction inside method A, method's B return address is going to be the instruction following the call instruction. That's where it's pointing. So in that place, we put a no-op with some data in it, and that data helps us find the metadata faster, including the frame size, and that made walking the stack much faster. But we still had to iterate over the OOP map data structure every time to find the oops, and that was quite slow. It was just a loop in C++. So we thought, okay, let's compile the OOP map into machine code that does the copying for us. So we don't need to iterate and parse the data structure. We just say every OOP map has an associated stub that knows how to freeze the oops or thaw the oops, and when we get to that frame, we just run that generated stub of code. That turned out not to be good enough, and this is sort of where we were in the last JVMLS in 2019, or it might have been 2018, I'm not sure. But so that year, let's say it was 2019, it came to JVMLS, and I had a conversation with Christian Wimmer, and he gave me an idea. He said, hang on, the requirement is that all heap objects need to be, their shape, where the oops are in them, must be stable. But they don't necessarily have to be the same for all objects, right? So a string might have an oop in one place, and I don't know, a date might have an oop in another place. So what we could do is allocate a new object for every frame. We don't need to know where the oops are. We just keep the same representation. So an object that contains a copy of the frame, and let the GC look at, so it's not synchronous with the actual freezing and thawing, but the GC in its own time, when it wants to scan the frame, it will find the return address. From that, it will find the metadata, it will find the oops, and even though that's slow, that's all done in the background. So those objects are always stable. And I asked the GC people, said, yeah, that could work. And even though it was immediately apparent that that can't be the solution, because obviously we're going to, for one, we're going to do a lot of allocations, right? We're going to have to allocate an object for each frame. But also, it doesn't quite solve the problem because we still need to parse the stack to know where every frame is to create an object for each one. And like I said, finding that metadata just to know how big the frame is, that takes a lot of time. But I love the idea because it was quite different from everything we had thought about before that. So we spent some weeks thinking about it, whether or not we could turn it into something useful. And then we realized that we could, and that was the big secret. And this is how continuations in hotspots are actually very efficient. So I said before that an object has to be stable. The shape of the object has to be stable. The oops can't change. But that's not entirely true. It's true from the moment the GC has first seen the object. So once the GC has found an oop, it must stay there all the time. But the GC doesn't look at objects all the time, only when it starts a collection. So we have a certain grace period from the time an object is created until the time the GC sees it, and where we can still change the shape. We can mutate it. And in fact, for some GCs, that is the entire young generation. We can still, the GC doesn't care about the stability of the oops. So what we could do, instead of parsing the stack and finding all the frames, creating objects for them, we take the entire portion of the stack. We still do lazy copy. I'll show you in a moment. We take the entire portion of the stack, we copy it into a heap object, but a new kind of object that we call a stack chunk. And that stack chunk contains multiple frames, and the GC knows how to read it and parse it and finds the oops in it. But then it's entirely mutable. Every freeze and thaw, we can keep copying things from it and back, and it's just a mem copy. We can do that as long as the GC hasn't seen the object. But once the GC has seen it, we sort of fix that stack chunk we can still thaw frames from it, because if we remove a frame, right, so an OOP, it's as if an OOP has become null. That's okay. As long as we don't freeze new frames into it, we never write a primitive into the same address. So once a stack chunk becomes old, once it's seen by the GC, we can no longer freeze to it. We can only thaw from it, but the next time we need to freeze, we'll just allocate a new chunk. And we don't need to do this for every frame, and it's quite rare that they actually need to do it. And it turned out that the copying itself, so we just need to do a memcopy. The copying itself is actually nearly free because we're copying inside the cache. At least one of the sides, so we have a continuation and we have a thread stack, at least one of them, where either just, so when we freeze, we've just executed those frames. Those frames are still in the CPU cache. Or the other way around, if we copy the frames from the chunk to the thread stack, we're just about to execute those frames. So we're basically copying inside the cache. And even though it sort of wastes some cache space, it is practically free, because that is what happens. If we didn't do any copying at all, we just change a pointer, and we were to say, now you're running from, now your frames are over there, the CPU also needs to copy all that data from memory to the cache. So actually doing a memcopy is virtually free. And that was a secret. And this is pretty much what we have today. So a continuation now is a linked list of stack chunks. And stack chunks contain any number of frames. And the continuation points to the most recent stack chunk, the youngest, containing the youngest frames. And this is what we do. First, I didn't talk about interpreted frames. We need to do some special stuff. We need to patch them in some way. But after a while, frames get compiled. So if we detect, and we have a very fast way, an ov1, just we have a flag on the thread, whether any of the frames inside the continuation are interpreted. So if they are, we go to the slow path and we do frame by frame. But otherwise, and this is a common case, we just take all the frames we need to copy. And again, it's not, we're using lazy copy, so it's not all the continuation frames. It's just the ones that we've just created. And if there is an already existing tail chunk, and if there's enough room in it, and if the GC has not seen it yet, we just do a memcopy. Otherwise, if there's not enough room in the tail chunk, or it doesn't exist, or it's already been seen by the GC, we allocate a new tail chunk and copy into that. When we need to thaw, the first thing we do is we try to see whether or not the thread stack has enough room for the entire stack chunk. We don't need to parse the stack chunk. We assume that we'll copy the entire stack chunk. Then if there are some interpreted frames, we go to the slow path. If the chunk has already been seen by the GC, we can do a copy, but we need to, in that case, invoke some GC barriers. It's similar to, I said, so thawing a frame from an old chunk is similar to writing nulls into an object array. And if the array is old, we need to tell the GC that those oops are gone, they're now null. So in that case, we do need to parse the frames and to invoke barriers. But otherwise, what we do is we have a certain heuristic. If the chunk is small, less than, I don't know, some arbitrary number, 1,000 bytes, we just copy the whole thing. We don't need to parse anything. We just do another memcopy. And if there are further chunks, so it's not the entire continuation, we add the return barrier. If the chunk is very big, we don't want to copy the whole thing, then we actually parse a single frame or a couple of frames and just copy them. But we don't care about the oops, we just need to know the frame sizes. And what does the GC do? So when a GC finds a stack chunk, so that's sort of a new kind of object, the GC says, okay, that's a stack chunk, the GC knows about it. The downside of this was that much of the change was in the GC. It says, okay, this is a stack chunk, I need to parse it. Then the GC parses the frames, it finds the oops. In some GCs, I think G1, because it traces objects many times, what we did is that after the first time we created a bitmap to help it find the oops the next time. ZGC doesn't need it. And that's it. It's all going on in the background. And because it's going in the background, we can do some actually more work there. And I'll mention it in a word or two later. Okay, so let's see what happens in that world when we have this huge stack I mentioned before. So we have this huge stack, and now we've just called yield. So the first time, we've just created all those frames, so it's OK to copy all of them. So we copy all of them, just a simple mem copy, into a new stack chunk. And that's it. It's actually very, very, very efficient. Now we want to thaw. We want to mount the continuation. But this is a big chunk. So what we do is we are just going to thaw a single frame or two, and then we place a return barrier. So when yield returns, it will hit the return barrier. It will thaw another frame. It will go to read sum, and then read sum again will hit the return barrier. It will copy over read loop, and this entire time we never needed to find the oops, but we did need to know the size of the frame. But now we're inside a loop, right? So read loop is going to call read sum again, and read sum is going to call yield again. But this time, let's say the chunk has been old, or we have a heuristic that the chunk is big. So what we're going to do this time around is we're not going to copy back to the same chunk, but we're just going to allocate a new chunk and copy it there. And from this point on, all we're doing is just copying that chunk back and forth, and it's a very small, very, very efficient mem copy. And yeah, this is just what we're doing. Just copying this entire loop, a single stack chunk, mem copy back and forth until the GC sees it, and then we might need to allocate a new one. And that's that. And we got amazing performance out of this. It's about the same as you would get with just a pointer switch. But there is something interesting we can do. The representation of frames tries to optimize for simple compilation. So we compile a method, and the compiler decides where to put the data, our locals, inside a frame. And it's not trying to optimize for memory at all. It tries to optimize for, I don't know, compiler convenience or speed or something like that. And when it comes to continuations, what we care most about is memory footprint. Because like I said before, the performance of virtual threads comes by virtue of being able to have lots of them. So the thing we care about most is memory footprint. But inside the stack chunks, we have the same representation of frames because we just did a mem copy. But what if the GC in the background finds those stack chunks and is able to compress them? And it compresses them to a very, very, very efficient representation. In fact, it can reduce the footprint by more than 50%. In fact, maybe even, we're not entirely sure yet, but maybe 70% even. And it compresses them in the background, and that is okay because if you remember, once the GC has seen a chunk, and it has in this case, we have to take the slow path anyway and find the oops and invoke barriers. We might as well do the decompression when we thaw the next time. So it doesn't add much cost, and this is one of the things we're working on, so that will drastically reduce the memory footprint of virtual threads. And that is, that's it.